Hello YouTube, welcome back to my channel. So this is the second series the second video rather in our series of introduction to computer vision and using convolutional neural networks and artificial neural network. Okay, so in this tutorial I'm just going in the last previous tutorial we built a model that was able to classify the iris dataset using artificial neural network. So in this tutorial we're actually going to go and dive deeper into computer vision. You're going to be classifying handwritten digits, but you're going to train a model that can classify handwritten digits. So you can train a model whenever you write a number, and then you give the model that number, right, like a picture of that number which is handwritten. Then the model can tell whether the number it's a 5, it's a 4 or 9 or something like that. So basically it just classifies a handwritten digit. So it's a very common problem in a computer vision, and I thought that we'll start with this before taking a deeper dive into convolutional neural networks and other stuff like that. So this is what you're trying to do. So for example, I have been showing you this picture, right? So in this GIF, right, it simply just represents a simple how a neural network trains itself to be able to classify handwritten digits. So you can see the number that is trying to predict is 5. So it has the input layer, the hidden layers, and then the output layer, which are the different classes of that of the numbers, right, of the different classes that our data set has. So we're going to be using a data set from Keras, and the Keras comes with this data set pre-installed already, so you don't have to do anything to get this data set. So this data set is just the data set of handwritten digits collected by from a lot of people, and Keras puts all this together. So it's just a 28 by 28 image pixels. So yeah, that's enough of it. So enough of the talking, let's actually get into the coding part. So I'm just going to say I'm going to import the data set. So from Keras dot datasets, you're going to be importing MNIST. So MNIST is a data set that you're trying to use. So MNIST is just a data set consisting of handwritten digits that are scale resized to 28 by 28 pixel handwritten image digits, handwritten images, digits. Okay, how do I say this? It's just handwritten digits, right? That's basically a picture of handwritten digits, and that data set is called the MNIST data set. So I'm just going to import something else. I'm going to import matplotlib. So matplotlib, you're going to be importing pyplot as plt. So we're going to be using that to visualize our data. So I'm going to say import tensorflow as tf, and then we can also import from tensorflow dot keras dot layers. So we're going to be importing a couple of layers. We're going to be importing I'm going to be importing a dense layer, and I've already talked about what a dense layer is, and also going to import the flattened layer, and I'm going to explain just a second what the flattened layer is. So I'm going to also import from tensorflow dot keras dot utils. I'm going to be importing normalize. So make sure I get the spelling of import right. Normalize. Okay, so normalize, and then also going to import from tensorflow dot keras dot models. We're going to be importing the sequential model, which is just going to be like a linear model, so sequential. And then also going to be importing numpy as np, and I'm also going to go ahead and actually ignore some warnings here. So I'm going to go ahead and actually import warnings so that we don't get those warning errors. So okay, and then I'm also going to include the magic method for matplotlib. So this matplotlib magic method will allow us to display our graphs in Jupyter Notebook. Okay, so just make sure you include that in case you're not getting the graph. Okay, so I'm just going to say ignore warnings. So I'm just going to put it here. So I'm going to do warnings dot filter warnings. Okay, I'm going to filter warnings, and I'm going to pass in here ignore, just like that, and this is going to import all of that, and then I'll actually filter that warning. So okay, I got an error here. So from tensorflow dot keras dot layers import tense and also flatten, and then there is no comma right here, so that's a syntactical error. So let me make sure I remove that. So now we have all our imports done. So now that we have our imports done, let's go ahead and actually load our data set. So the error still came, so this actually didn't work. It worked on my other computer. I don't know why it didn't work over here. Okay, so let's just ignore some warnings. Just don't worry if in case you get them. Okay, so now that we have that, let's go ahead and actually load our data set. So I'm just going to make a markdown here. So I'm going to say load. I'm going to load data set just like that. So okay, I think the filter warnings, that's what didn't work. So filter warnings. Okay, I forgot an N there, so that's a spelling error. So filter warnings, and then we can run that. You can see now we don't have those warnings. That was the cause. So now that we have that, let's go ahead and actually import our data. So we're going to say xtrain y underscore train, and then comma another tuple, and then this will be x underscore test and y underscore test, and this will just be mnist.load underscore data. So this is going to load for us that mnist data set. Okay, so great. So this is just an the data set. We're going, this is going to be the training. X train is going to be y train. It's going to be x test, and then the y the x test, and then the y test. So we're going to be using this for training and testing our model. So let's go ahead and actually see what's the shape of this data. So I'm going to go x underscore train dot shape. So I'm going to run that, and it's going to return to me the shape of this data set. So we have about 60,000 individual pictures, and each picture is 28 by 28 pixels in dimension. Okay, so you can also do that with the x underscore test, and then you can do dot shape. This is also going to return to the shape, and then the testing is 10,000 individual data pictures, and it's also 28 by 28 pixel images. So now let's try to visualize these images. So I want to see how these images look like. So I'm going to just plot it here. So I'm going to create a figure, and I'm going to give it a figure size, and the figure size is going to be a tuple. Let me put in here 15 by 7, and then I'm going to do a plt.imshow, and then I'm going to pass in here my image. So I'm going to just display x underscore. I'm going to, this is going to be an array. I'm going to get the maybe the 9th element and the 8th index, and then I'm going to pass in a CMap here just to make it look good, and then I'm going to do a plt.get underscore CMap, and then I'm going to pass in here gray. Okay, so now that we have that, I'm simply going to do a plt.show just like that, and this is actually going to, okay, I got the fixed size wrong, so there's no underscore here. It's actually an equal sign. Okay, sorry for that. Just maximize this. Okay, so this actually delete that, and then we put an equal sign. So make sure I run that, and you can see this is actually an image of 4. So if I change this to be let me change this to be 19, then this should be a 9. Okay, so we have different images. So you can just play with this, and you can see the different handwritten images. So this mnist data set consists of handwritten digits, which is about 70,000 handwritten digits. So from between the number digits of 0 and 9. So that's what you can get. So you can just change these values at the different indexes and then visualize that image. So that's basically how the handwritten digits look like. Okay, so you have white and a black image. The white images have a pixel value of 255, while the black one has a pixel value of 0. Okay, the reason I'm explaining this to you is just a second. Let me just write this code and I'll explain to you. So I'm going to go xtrain, and then I'm going to get the element at index let me get element at index 1 over 0 is fine. So I'm going to run this. So you can see the parts that have that are completely have bigger values are the parts that are white in the image, while the parts that have 0 value are the parts that are black in the image. So you can see right here, right? So this is actually a white spot in our image. This is a white spot in our image, and then the bigger the value is, the more whiter it is. So the maximum is 255 and the minimum is 0. So the numbers of pixel values of a black and white image are ranged between 0 and 255, 0 being the darkest, like black part here, and 255 being a white spot on our image. So any number between is a variation of that gray or black, right? So any number between is between a black and a white, right? So the different numbers represent the intensity of the white. So for example, 50 is less darker compared to 159, because 159, the bigger the value is, the more whiter the spot, and the absolutely biggest value you can get is 255. Okay, the reason why I'm explaining this to you is that these 255 and the other numbers are actually very big values to use to train our model. So what I'm simply going to do, I'm going to normalize our data, and normalization, what you're simply going to do is you're going to take each individual pixel value and divide it by the maximum value, which is 255. So we'll get the value between the scale will be between 0 and 1 instead of 0 and 255, which is very large and can take a lot of time for our model to train, and our model won't convert properly. So using a smaller value between 0 and 1 will make our model to perform better on the training, so, and also the classification, give us a great model in overall. So what you're simply going to do, remember we imported the normalize here, so we're going to use it down here. So what you're simply going to pass in, I'm going to pass in here, and I'm going to pass in x underscore train, and I'm going to say axis, and I'm going to assign the axis to be 1, and also going to do this for the x test, and this is going to be normalized, and I'm going to pass in here x underscore test, and then axis, the axis is going to be 1, just like that. So great. So that is going to normalize our data, means it's going to fit our data between 0 and 1 instead of 0 and 255, because that will make it easier for our model to train and to converge. So great. I hope you understand why we are normalizing the data. So now if I do x underscore train, and I get here I got the value of it at index 1, so I'm going to get the image at index 1 again, and you can see now instead of us having those very large values of 255, we have values between 1 and 0. So all these large values have been scaled down to decimal points, 0 point something. Okay, so great. So now our data is normalized. This will make it easier for our neural network to train on and to fit better on compared to having very large values. So now that we have that, let's go ahead and actually begin to train, or let's call it build model. So we're going to build a model. So we're going to now build our model. So I'm going to go ahead and actually create a variable called model, and this is going to be sequential, and sequential we imported this from Keras, right? So model.add, I'm going to add in a layer here. So I'm going to before I add in this, let me just explain something too. So I'm going to bring you back to this image. So our image, our pictures, right, our images, right, are 228 by 28 pixels, right? So these are 28 by 28 pixels, and these are the total number of images that are there, but each image has a pixel value of 28 by 28. Now this is a two-dimensional array. As you can see, this is a two-dimensional array. We can fit a two-dimensional array to our neural network, right? Because our neural network is more like in a one-dimensional, like the arrangement of the neurons, right? It's a more like one-dimensional linear way. So what we'll simply do is that we'll multiply the rows by the columns, basically, which will be 28 pixels by 28 pixel, meaning that you're going to take our two-dimensional image and turn it into a one-dimensional image, and then that we can fit that into our model, right? So we're going to take the pixel which is going to be a square image like this. So we're going to multiply the number of rows, the number of pixels making the rows by the number of pixels making the column, which is going to be 28 by 28, which will give you a total of 784 neurons. So the input layer going to have 784 neurons. Okay, and that value comes from multiplying the total number of pixels that make the dimensions of the image, which is 28 by 28 image. So we're going to simply create a flattened layer to do that for us. So that's why I imported the flattened layer. That's what the flattened layer does. So I'm going to say flatten, and then I'm going to say input underscore shape, and the input shape is going to be a tuple. I'm going to pass in 28 by 28. So this is going to take that 28 by 28 image and then flatten it into a one-dimensional image of having 784 of individual pixels arranged in a linear fashion. Okay, so you can feed that to our neural network. So now that I have that, I'm going to model.add, and I'm going to add a dense layer. So the dense layer, we're going to add it here. We're going to make it number of units in here. We can say any unit. I'm just going to say 130. I found that number to work for me, right? And I'm going to also say activation. I'm going to set the activation function to be relu. Great. So I'm just going to bring you back to this image here. So this is going to be our flattened layer, which is going to be 28 by 28, which is going to be 28 times 28, which is going to be 784. And then we're going to have a dense layer, which I said is going to have 130 neurons, perceptrons, so you can say neurons or units. And then we're going to have also another layer, and then finally we have the output layer. So let's go ahead and actually create the second hidden layer. So the second layer, I'm just going to copy this and just copy it and paste it again. So I'm going to create another dense layer of 120 units. So now I'm going to create the final output layer. The final output layer needs to have 10 neurons, and these 10 neurons are the total number of classes that our image can have. So if I go in here and then create a value up here, another cell up here, and I'm going to do y underscore train. The y underscore train is just an array that tells us which are the labels corresponding to those images. Okay, that's what basically it tells us. So for example, in here we printed we printed at x train at element at index 19, right, the image at index 19. So if I move down here and I try to access at index 19, it tells me the value is 9, and indeed when I look at the image, that's a 9. So that's the individual labels that these images have. Okay, so there, if I just go, let me just try to get dot unique. So if I run that, I think this unique is a method. So if I run that, it actually doesn't work. So I think I need to convert this into an array. Let me just check that if it is a numpy array. So it's already a numpy array, so let me just try to, it's already a numpy array. I don't know why numpy dot array. Try to get the unique values. Okay, so dot unique, and then run that. So it doesn't still work, so I don't know if it's an attribute or something. So it doesn't really work. So what I was trying to simply show you is the number of unique values within our array. So the unique values is just they are going to be from 0 to 9. So the array, these are the individual classes. So that's why we need to have an output layer having 10 neurons. To each neuron will be the value for each individual class. One neuron will be for 0, and then when that neuron is activated, we can get the probability of that neuron, and then get the probability of all the other neurons in the output layer, and then we can see which neuron has the biggest probability. So the neuron that has the biggest probability, if it's neuron 9, then that value is probably, that picture is probably a 9. If the neuron with the highest probability is a 5, then that neuron is a that picture actually happens to be a 5. So I'm going to do model.add, and I'm going to add in a dense, and then this dense is going to have units. So I'm going to say units, and the unit is simply going to be 10 units, and then I'm going to have an activation, activation, and the activation is going to be relu. Great. So now that I have that, I'm going to go ahead and actually compile my model. So I'm going to model.compile, and then I'm going to compile that model. So I'm going to compile that model here. I'm going to say optimizer, and the optimizer is going to be Adam. The optimizer is going to be Adam, and then you're going to go ahead and actually pass in the loss, and the loss is going to be sparse underscore categorical underscore cross entropy. So sparse categorical cross entropy. Okay, make sure you get the spelling right. So sparse categorical entropy, that's going to be our loss, and then I'm going to pass in my metrics. I want to get the accuracy of the model, so I'm going to pass in here accuracy. Great. So now that we have them, so I'm going to run this, and then we have an error. Let me see where the error is. So unknown metric accuracy. So accuracy, I got the spelling of, no, that's actually right. Accuracy, I got the spelling wrong. So like that. Yeah, so now that we have that, let me go ahead and actually begin to train our model. So just going, okay guys, now that you have done the compiling of the you have set the attributes for the different parameters for compiling, we can go ahead and actually train our model. But before we do that, I can see I've made a mistake. It is actually soft max. The reason why we are using soft max is that we have different neurons, right? We have on the output layer, we have different neurons, which are 10 different neurons. Now each of these different neurons is going to produce a probability. Okay, now we want to look for the neuron that has the maximum probability. Now for us to be able to get the probability from each neuron, that's why we're using softmax. So the softmax will enable us to get the probability of each neuron, and then from the probability of each neuron we can decide which has the highest probability, and then from there we can classify our image based on that probability. So if for example 0 has a probability of 0.4, and then 9 has a probability of 0.6, then and 0.6 is the biggest, then that digit is actually a 9. Okay, that's why we're using softmax here. So softmax will enable us to get those different probabilities. So now let's go ahead and actually train our model. So I'm just going to make this a markdown, and then I'm going to say train model. So I'm going to just go ahead and actually train our model. So I'm going to create a variable called hist, and I'm going to store in our model here. So I'm going to model.fit, and I'm going to, oh sorry, I pressed the wrong key again. I'm going to go ahead and actually pass in the different attributes. So I'm going to go x underscore train, and then you're going to use y underscore train. Since we're going to use this to train our model. Then I'm going to pass in the validation underscore data. This is going to be a tuple of x underscore test, and then y underscore test, just like that, just like this. And then I can now specify the number of epochs that we want. So I've already talked about what an epoch is, right? So I'm just going to go ahead and specify my epochs. I'm going to specify an epochs of 4. The reason why I'm not training this model so much like in the previous tutorial, I trained up to I think 100 epochs, I believe, is because this image handwritten image digit classification is actually a very simple problem in machine learning, and you can solve this using traditional machine learning algorithms like the k-nearest neighbors and the support vector machine. But using a neural network is a bit of overkill. That's why you don't need to train it so much, and you'll be able to also get a great accuracy. So that's why I'm just setting it to 4 epochs. In case you train it and you want more accuracy, you can increase the value, but make sure that you don't do overfitting. Okay, so now I'm just going to put it 4, and I'm going to go and actually train that model. So this is going to train my model, and then once this is done, I'll resume the video and I will continue from there. Yeah, hello guys. So you can see that I'm back, and you can see that I didn't actually run this cell after changing the value before running this. So that's it. You use the ReLU value. That's why you can see our accuracy is very poor. So that also emphasizes the importance of using softmax. So if you use your ReLU, then you get a very wrong accuracy. You get a very low accuracy. So you can see mine's about 9% accuracy. Now that I have changed this into softmax, okay, now let me just remember to run this cell, run everything before that. So now the model is going to train again, and you can see the accuracy is already increasing. So that's my bad. I didn't actually run this cell after changing this into softmax. So make sure that you run that cell before running this cell, and then I'm going to pause the video here, and then I'll be back again when this has finished training. Okay guys, now you can see that our model has completed training, and you can see that you have a very great accuracy. Now accuracy increases as we train more and more, but be careful not to train too much, because there's something known as overfitting. So your model might overfit, so don't just put in a very high value thinking that you reach 100. You might reach 100 with a training set, but with a prediction you'll do actually very poor. Okay, so be careful that you don't actually overtrain your model. Okay, so just 4 epochs, 5 epochs, 6 is enough. Just keep it below those values. Okay, but feel free to experiment and do what you want. So now let's go and actually make some predictions. So I'm going to change this into a markdown, and I'm going to just type in here predictions. Okay, so predictions. And if you want to change a cell into markdown, you just select that cell and press M on it, and then that will change it to markdown, or you can simply come in here and change it into a markdown. Okay, and if you want to change back into a code, you just select also code here. So great, now that we have that, I'm going to go ahead and actually make a prediction. So I'm going to call it prediction. This is going to be model.predict, and I'm going to pass in I'm going to predict x underscore test, and I'm going to predict the value at the 23rd index, and then I'm going to now do a reshape. Now the reason I'm going to do a reshape is that remember when you pass in the, let me just scroll up here, then I show you the shape of that image. Whenever I do shape, right, you pass in a three-dimensional tuple, right, like the first value, the second value, and the third value. So the last 2 values are the dimensions of the image, which is a 28 by 28 pixel image, and then the first value here, which is 360,000, is the total number of images that we have. And now here, since we have to now pass in a similar tuple, so what I'm going to do, that's why we're doing a reshape. So I'm going to pass in 1, which indicates that this is only a single image, and the dimensions are 28 by 28. So that's what you need to pass in. So I'm going to run that. This is going to return to us a prediction. I do predictions, and then I run that. You can see this is actually an array of 10 values. So let me just do the length, and then do the length, and then you can see. So the reason why the length, okay, it's actually returned to me. Let me see, just print this out. You can see it's actually an array of an array. So let me just do I have to do length, and then I'm going to do length of the first index. So let me try to run that. You can see it's actually 10. The reason why it's 10 is that because in the output neuron we have 10 individual neurons, and each individual neuron corresponds to a specific classification, so 0 through 9. Okay, now if I just remove this and just get predictions itself, prediction, and then you can see that this is actually some values. So now how do we classify these values? Like, how do we get the values, like which of those values is bigger? Because the one with the biggest probability is actually the value that the classification wants to output. So for example, if the biggest value here, the biggest neuron with the biggest probability is 9, then the digit that was passed in the input layers will be 9. Okay, so let me just go ahead now to get that in NumPy. You just have to say np.argmax, and then you pass in your prediction. So it's going to return to you the index having the highest probability, like the index of the highest number in this array. Okay, so I'm just going to run that, and that index will correspond to the number that we are trying to predict. So it's going to correspond to the output. So if the output here has the for example, in this space, right, argmax returned to us 5, meaning that the neuron 5, right, has the biggest probability. So the image that was probably passed in is probably an image 5. So now let's try to visualize this. So I'm going to do a plt.figure, and I'm going to pass in my fig size, and I'm going to just pass in tuple here. This is going to be 12 by 7. Okay, these are just some values that you can change, and then plt.imshow. So I want to do an imshow, and then you're going to pass in x underscore tests, and then I'm going to go 23. Okay, and I'm going to pass in that value 23, and I'm going to now say cmap, pass in the cmap, that is going to be the color map. In the color map is going to be plt.get underscore cmap, and then I'm going to pass in here gray, just like that. And then I'm going to do plt.show, and then I'm going to now go ahead and actually show that image. So you can see the actual image is a 5, and indeed our model predicted 5. So you can actually change these values around, and then let's predict 30 here, and then also change this to be 30. So let me now make it a prediction from that, and it says 3. So if I run it, you can see the image is actually a 3. So that's how you can do a handwritten digit classification using a neural network in Keras. So that's basically it for this tutorial. So in the next tutorial, we'll begin to dive deep into deeper concepts in computer vision. We'll begin to look at convolutional neural networks and the transfer learning and other things like that. And then in the upcoming videos, we'll actually build different projects to classify different images. So guys, thanks for watching. If you like this tutorial so far, give it a thumbs up, subscribe to my YouTube channel for more videos like this, and if you don't like the video, give it a thumbs down and let us know in the comment section why you don't like the video. And if you have any feedback on different data sets that you think we can work with in this series, please kindly drop a comment section below, and I'll do my best to follow up on that. So thanks for watching. See you in the next one. Keep safe.